Hey there, Geometry. Let's look at Lesson 13 in Unit 3, using the Pythagorean Theorem and Similarity. So here it says, is triangle ABC similar to triangle CBD? So let's look at what that is actually talking about. ADC is this one. And CBD, do that one in pink. CBD is this one. Are they actually similar? So if I draw those, I'm actually going to put this oops, not that, pen. A, D, C, and C, B, D. I know angle A is congruent to angle B. Angle D is congruent to angle D. And angle C, which we're comparing those two, they're not calling them the same, like they're not the same angle, okay? One of them is that one, and one of them is this one when they say C. All right, no, let's rewind all of that. I just looked at, 1 second. So let's try that again, because I see a mistake I made. A, D, C, and C, D, B. So angle A is 53 degrees. All right. Angle D is 90 degrees. And angle C, this angle C is 143, 737. All right, now let's do the pink one. Angle C is this one. I don't know what it is, but I know that 90 plus 37 353. And then B is marked as 37. So it says, are they similar? Well, I have angle, similarity. Similarity. So yes, they are similar. And actually, yeah, I had to do the subtraction to make sure, but once I do the subtraction, I didn't have to do it again if you notice that all the numbers are the same. But yes, they are similar. And we could write a proof about that, just stating that angle A is congruent to angle C. Actually, I wouldn't go that way. First, I would say that angle DCA is 37 degrees because the sum of interior angles in a triangle is 180. And then I would say that angle BCD is 53. Ditto, same reason. Angle ADC is equal to 90, and angle BDC is equal to 90. Perpendicular lines make 90-degree angles. Now I can say that all the angles are congruent. Angle A is congruent to angle B. Using substitution, because angle A is 53, BCD, Angle A is not congruent to angle B. Angle A is congruent to angle DCB, or BCD. So we know BCD equals 53, so we can substitute angle A here to use it in that statement. Okay, so we know those two are congruent, and now we can say the 90-degree angles are I just did that twice. ADC is congruent to BDC, substitution, because they're both 90 degrees. See right here? I've got one equal to 90 degrees, the other equal to 90 degrees, so I can substitute and use it in that reason. So now we know the triangles are similar. Triangle ADC is similar to CDB. CDB, because of angle similarity. Cool. We didn't have to go through the proof there, but I wanted to give you a basic outline for the proof. Okay, two tangled triangles. Trace the two similar triangles onto separate pieces of tracing paper, which we can't do. But we just did, like most of the things we're going to do in this example, we did above. So we're going to talk through them one more time and make sure that we all understand them. Trace the two smaller triangles onto separate pieces of tracing paper. I'm going to line them all up. When we talk about, let's say this, when we talk about right triangles, we talk about a short leg, a long leg, and a hypotenuse. The hypotenuse is always across from the right angle. Short leg, long leg, and hypotenuse. Always. That's how a right triangle works. I have a short leg, a long leg, and a hypotenuse. And the hypotenuse is always across from the right angle. So let me redraw these next to each other. Okay, this is G. My short leg is right here. Okay, my long leg is right there, and my hypotenuse is right here. So my short leg is HG. G is the 90, there is H. My hypotenuse is HE, and it is 12. And my long leg is GE, which we already have. Angle H is 53 degrees. If we did the math, we know the angle E is 37 degrees. Now let's draw the other one. I'm purposely drawing it a little bit bigger. Angle G is still the 90-degree one right here. This is my long leg. This is my short leg. And that's my hypotenuse. So long leg goes GF. Short leg goes GE. And what things do we know? We know an angle F is 37. Therefore, we know angle E is 53. G is 90. Do we know any measurements? The hypotenuse is 16. Okay? So I just separated, I split the triangles into, and I lay them up next to each other so you could see all the short legs are the same place, the long legs are the same place, and the hypotenuses are in the same place. Hypotenuses. And we would do this with tracing paper if we were face to face. So I can convince myself that they're similar because I have angle, triangle similarity theorem. Okay, this H is equal to that E, and this E is equal to that F. I would always use 3 letters to name those angles, though. Okay, write 3 similarity statements. I can say triangle HGE is similar to triangle EGF. Pause for a second. I'm going to see what we're going for here. Yep, we're just naming them in different ways. Triangle GEH is similar to triangle GEF. I just went GEH. Oh, that's not right. Hold on. HGE, HGE, EGF. GEGF. Yep, and now I went GEH, GEH. I need GFE. So those are not correct. Sorry about that. I'm sure you caught that. And now one more. It's just another way to write the triangles. So I just did HGE and then HGE, and then I did GEH, HGE, GEH. Now I'm going to do EHG. Gets a little wonky when I draw all the way over here. So EHG goes FEG. Okay, that's just 3 different ways to name the same similarity. And as long as you track the same vertices, if I look at this one, let's change colors. That means that angle H is congruent to angle E. Angle G is congruent to angle G, and angle E is congruent to angle F. All right, if we check that out. H is congruent to E, G is congruent to G, and E is congruent to F. All right, we're just naming the congruent angles in the correct order. All right, now determine the scale for each pair of triangles. If I go from this triangle to that triangle, my scale is going to be 16 over 12. EF corresponds to HE. And if I'm getting bigger, I want my scale factor to be a number bigger than 1. 16 over 12 is bigger than 1. If I simplify that, I can divide by 4. It's 4/3, or 1 1/3. Now if I'm going smaller, I want my fraction to be smaller. I would do 12 over 16, which is 3/4. And that number is between 0 and 1. So that's my scale factor. It's 16 over 12 or 12 over 16. And to simplify that, it would be 4/3. Let's make that the same color. I know you guys can follow whether I do different colors or not, but I like it when it's sort of the same. 12 over 16 or nope, that's not what I meant to do. Let's erase that. I meant to simplify the fractions. Sorry. 4/3, 3/4. Okay, so that's our scale factors. Determine the length of the other sides. So I'm going to go, if I multiply, let's see, well, we need one more side. Do I not have, let me erase this. Maybe I'm missing something. No. Okay, hold on a second. I have forgotten one very important fact. Okay, I'm going to go in green. So you guys need to go back and listen to this part and apply it because I've made a mistake. Okay, I need to include this triangle. Okay, now that one's going to be bigger than the other two. My right angle is E. My short leg right here is 12. And it goes up to H, which is 53 degrees. And my long leg is 16, and it goes over to F. And that is my hypotenuse. But I can figure out the measurement of my hypotenuse because we know the Pythagorean Theorem. 12 squared plus 16 squared equals c squared. 12 squared is I get summertime brain sometimes. 144, 256. So add those together, and I get 400. Take the square root of both sides, and I get 20. Yep. So this hypotenuse is in fact 20. All right, so I need to change these. Ooh, that was cool. So we compared, what's written there in black, we compared these two triangles. Now I want to compare other two triangles. So let's compare the green one and the small one. So that would be triangle HEF is similar to triangle HGE. So I did HEF to HGE. So I compared the two littler ones. I compared the big and the little one. Now let's do the big and the medium one. So triangle HEF is similar to triangle EGF. That's what we mean by three similarity statements. I knew something was a little wonky when I tried to do it. Those are my similarity statements. So determine the scale factor for each pair. So I'm going to erase this, and we're going to go one more time. So HGE to EGF, these two. I'm going bigger, so I'm going to go 12 to 16, or if I went smaller, it'd be 16 to 12, which is the same as 3/4 or 4/3. Now let's do this one. I'll change to blue, not that. So HEF to HGE, that's the big one, to the small one. So I'm going to go smaller. So that means that I should have a small, and I'm going to pick 20 to 12. So I can do 12 over 20, or if I went bigger, 20 over 12. And if I reduce those fractions, let's just cut them in half because they're both even first. That's not small enough. Cut them in half again, 3/5, or 5/3. Okay, those are my scale factors. And then the next set of scale factors, and that's the big and the medium. I can do, sorry. That's not working. I was trying to undo my scribbles. Sorry, we're going big to medium, so my numbers are 20 over 16 or 16 over 20, which simplifies again, 5/2, or I'm just cutting them in half. Oh, that's not half. I forgot how to divide by 2. It happens. Cut in half, 10 over 8, cut in half again, 5/4. 8 over 10, 4 over 5. So those are my scale factors, okay, the last sets. All right, now determine the lengths of sides HG, GF, and HF. Let me get my highlighter out. HG, we want to determine this length. GF, which is this length, and HF. HF, which I already did, using Pythagorean Theorem on that one. So we got HF is 20. Now let's do HG. Okay, so this one is unknown. Let's just name it X. And let's compare it to something that we know. I can't compare it to this one because we don't know EG. Those are the corresponding parts. If I don't know EG, I can't solve HG. But I can compare it to this one. Okay, it's like the parent triangle. 20 and 12 are given. 12, and I don't know what. So that's what I need to compare it to. I can use the scale factor, and that was big to small, which was this one, big to small. That was my scale factor of 3/5 or 5/3. So if I take my known 12 and I multiply it by the getting smaller one, which is 3/5, I can get my new measurement. 12 times 3 is 36/5, which I certainly don't know. 36 divided by 5, 7.2. So we have that one, it is 7.2. And now we want HGGF. So we want this one, let's call it Y. I need two triangles that have the given sides measured. And again, it's the big one and the medium one, because it's 20 and 16. And then the unknown side has to have a corresponding one that's already measured, so 16 and Y. So again, we're going smaller. So HEF and EGF is right here. That's my scale factor, and I want to use the going smaller scale factor, which is 4/5. So my given measurement is 16 right here. Because I don't know Y, I'm getting smaller, so I want to multiply it by 4/5, because that's the fraction between 0 and 1. 16 times 4. 16 times 4. 64/5. 12.8. Pause. We now have enough information for all the triangles to solve the third sides using Pythagorean Theorem. All right, we're not going to do that right now, but we have all the information. Something I want to point out is when I was solving x, I used the scale factor exactly as it is. I can also set up proportions, which I've always found is easier, and you can pick. So when I'm solving for x, I used 20 and 12 and 12, and I don't know. So I can set up that ratio as just 20/12, which is this one. 20/12 is the same as 12 over I don't know. And I can cross multiply or multiply down. So I get 20x equals 144. Divide both sides by 20. I should get up and go get my calculator. 144 divided by 20. And I get 7.2. Same thing. All right. I like that better than using the scale factor personally. Now when we're trying to solve for y, I'm going to do 20/16 equals 16 over I don't know. So 20/16 equals 16 over y. Cross multiply. 20y equals 256. Divide both sides by 20. It should be 12.8, but let's check. 12.8. Okay, let's move on. It's getting a little long. More tangled triangles. So convince yourself there are 3 similar triangles and write a similarity statement for the 3 triangles. All right, I'm going to pause and pick this triangle apart, and I'm going to ask you to try to do the same thing. So draw those 3 triangles, the big one, the medium one, and the small one, with the short legs, the long legs, and the hypotenuses. So I just redrew those 3 triangles. The biggest one is the ABC. That's the biggest one drawn there. And then I found all the corresponding sides. So that's this one, where this is the long leg, that's the short leg, and that's the hypotenuse. And I put all the pieces down here, okay? Then I picked apart the medium one. which is this triangle right here. Okay, D is the right angle, which is why I put it right here. And this is the long leg, that's the short leg, and that's the hypotenuse. So the short leg I knew was 4.6, so I wrote 4.6 there. And then the bitty bitty triangle. D is the right angle, forgot to mark it, and this is the hypotenuse. So I marked it as 5. Now write as many equations about the proportional side lengths as you can. I know that AC over CD equals CB over DB equals AB over CB. So I just compared all the side lengths to this one and this one. And I could actually keep going. Let's do there's so many that I could write. I could say that AC over CD equals CD over AD equals AC over AD. So I compared the short legs of all of them. They should all be proportional. I could compare all of the hypotenuses. AB over CB equals CB over AC equals AB over AC. I compared all the hypotenuses. Okay, lots of different ways that you can write the proportional because each triangle is similar to each other. We proved that in the last problem. Therefore, all the side lengths are proportional. And what do we notice about these equations? It's kind of magical. Let's see. Those are the same. Let's see, I think this should have been a D. Let's see, AC over CD, CD over AD, AC over AD. Yep, that should be an AD. I'm just seeing a pattern here. Let's see, I can write that last one. The long leg, CB over DB equals DB over DC equals CB over DC. So it's the same pattern for each one. AC is on the top, AD is on the bottom, and CD sort of goes diagonal. AB, AC, CB, CB, DC, AB. Just that pattern. I think we're going to get somewhere with it here in a second. So what do I notice? There is a pattern. And that's all we're going to do with that for now. Again, if we were in the classroom, I would take this one step further because there's a pattern that works for all of them. But rather than go that way, I think that may confuse more than help. But just know, if you have, this is a triangle that I can split. I can split it into 3 similar triangles, a large, medium, and a small. All of the triangles are similar, therefore all of the sides are proportional. And that is it. Nice job.